Hello everyone. Let's wait for 5 more minutes, then we'll start today's class. Hello everyone. Are you able to hear me? I'll just share my screen. Are you able to hear me properly and see the presentation? Am I audible to you? Anyone from the class? Shailendra, am I audible? Is the presentation visible to all of you right now? Shailendra, are you there? Is anybody there? Should I start the class or my screen is not visible? Please confirm someone so that we can start the class. Then let me start today's class since no one is responding. So this is lecture number 9 of material characterization course provided by Professor S. Sankaran from IIT Madras. And this is me, Dorothy Sachdeva. I am pursuing PhD from MRC department at Indian Institute of Science. Since we in the last class we were discussing about the TM and how the diffraction and how the X-rays are used for the characterization of your material. So we will do the continuation part of the previous classes. We will study how the X-rays are being used, how the diffraction is being used for the characterization. So in last class, we discussed about the Scherrer formula. So when can we use this Scherrer formula? The Scherrer formula can be used when the crystallite size of your material is less than 5,000 angstroms. This we discussed in the last class. We discussed like this, that T is equal to 0.9 lambda divided by B cos theta, where in this equation your K is a constant which is generally taken as 0.9, or you can say 0.89, and your lambda is your wavelength. T is basically your thickness of crystallite, and depending upon your thickness, you will have the broadening of your XRD peak, and your lambda is your X-ray wavelength. B is here is your FWHM. FWHM is full width at half maxima. Suppose this is your maxima, so half of this will be here. So the width of the peak at this position will be your full width at half maxima, FWHM. And this is measured in terms of radians. And then you have this theta b as your Bragg angle. In generally in X-ray, you have on x-axis you have 2 theta value, and on y-axis you have intensity. So from those 2 theta value, this where the peak will exist, you will have your 2 theta b value, and the broadening will tell you about 2 theta 1 and 2 theta 2 value. So this theta b, 2 theta b will be your double of your Bragg angle. So using this equation, you can calculate if you have your XRD pattern like this, you can calculate if your peak is very narrow or if your peak is broad, you can calculate the size of your crystal only when its size is less than 5,000 angstrom. So if the crystallite size is if the crystallite size is more, that is larger I say, then your FWHM or your peak will be sharper. And if your crystallite size is more in nanometer regime, then your peak will be much broader as compared to your bulk sample. So using this thickness of your peak, you can calculate the crystallite size. Next is this residual stress measurements using X-ray diffractions. These X-ray diffraction we discussed in the last class can also be used for the stress measurement, and stress will lead to your strain. So basically, we will not go into much detail of this stress strain thing, but you all know that sorry, but you all know that stress in certain direction, suppose y direction, will be given by force per unit area, and this will lead to your strain in y direction, which will be given by delta L by L. And the relation between stress and strain is also given by Hooke's law, which is sigma y is equal to constant E into epsilon y. So this is your stress, this is your strain. So basically, the shifting of the peak represents how much strain is present in the system. So if your crystallite is having no strain at all, then it will have a perfect peak at 2 theta value, just as shown in this figure. But because the despacing here in the crystal is the standard value d naught which we were expecting for our system. But if the strain is uniform and the despacing between the two planes d naught have been increased in the all the crystal uniformly, then it will have a shift if the shift at a lower theta value. When the strain is uniform in the crystal, then your peak, XRD peak, will get a shift at a lower theta value. And when your crystal is having the non-uniform strain, then you will have a very less intense peak and it will be much broader like this one. So depending upon the shape and position of the peaks, you can find out the strains present in your system. This you all know that the unit cell of the crystal system will be reflected by the line positions. Lines positions means where at the 2 theta axis at or at x-axis your peak is present. If your peak is present at this 2 theta value or at this 2 theta value, it will depend upon the dimensions of your unit cell and the atom positions. Like if the atom is present at which position, that will depend upon the intensity, and intensity is given by your y-axis. So the peak, if it is having higher intensity or lower intensity, it also means that your atom positions could be different in different cases. So basically, one more thing which I would like to add in this stress strain thing, that we can use uh, these uh, the combination of the size from this Sherrod formula and the strain can together be used to form your Williamson Hall plot, or it's sometimes written as WH plot. Here we plot a graph between B cos theta and sin theta. You can get, while considering both the size and strain components, you can have for a single component a peak like this or like this. If where you can have the equations of B cos theta for size as 0.9 lambda divided by T, and for strain you have B cos theta is equal to minus 2 delta D divided by D into sin theta. So if I'll just write it here, if size is only contributing, then your b cos theta will be a constant value. This one, this which I am broadening over here in your WH plot. This will be a horizontal line. And if your strain is the only contributor, is only contributing, then you will have b cos theta as a linear function of sin theta, which I'll try to change the color. Yeah. So if only strain is contributing, then you will have a linear line as a function of sin theta. So this b cos theta will follow this green line. And if size is the only contributing factor, then your b cos theta will have a constant value, which will be represented by the horizontal line given by this red line. Is this thing clear to everyone? Someone please reply. Are you able to understand the things? Oh, okay. It means here my screen is visible, no? I'm clearly audible to you as well, right? Sarvana Devi, can you please reply? My screen was visible and I was audible clearly. Okay, okay. Thank you. Okay. So if this thing is clear, then we'll go to this next thing, XRD. This XRD is used basically, the line position will tell you about the unit cell and the line intensities will tell you about the atom positions of present in the crystal system. I'll just try to erase this. Okay. So since we all know XRD is used for the crystal structure determination, basically, you all know this Bragg's law where your D is equal to lambda divided by 2 sine theta. We simply know Bragg's law as, sorry, and lambda is equal to 2d sine theta. And when we rearrange this, we can get this d is equal to lambda divided by 2 sine theta. And for the cubic system, we have DHKL is equal to A divided by under root of h square plus k square plus L square. So using these two equations, we can simply write the sine square theta divided by, wait, let me make it much more clearer. So using this Bragg's law, where we write n lambda is equal to 2d sine theta on the right hand side, we can just write that your sine theta is equal to lambda divided by 2d, right? So using this equation and using this equation for the cubic system, where your d value is given by a divided by under root of h square plus k square plus L square, we will combine these two equations. Then we will write sine square theta is equal to lambda square divided by 4, and your d is given by a square into h square plus k square plus L square. This h square k square L square will go on the opposite side of your equal, and it will give you this equation where your sine square theta divided by h square plus k square plus L square, which I have written already in the PPT, will be equal to lambda square divided by 4a square. And your h square plus k square plus L square is written basically as s, which is always the integral. This is your s term. So this s will now be represented instead of your square of your sums of your planes. So instead of writing h square plus k square plus L square from now on, we'll just simply write as small s. So this s is always an integral, and your lambda square divided by 4a square is a constant for any one pattern. So basically, you will have certain specific values of s from which you can calculate which planes will be allowed and which one will be not. And it's written over here that the planes, the integers such as 7, 15, 23, 28, 31, etc. are impossible because they can't be expanded in the form of h square plus k square plus L square. It's written as certain integers such as 7, 15, 23, 28, 31, etc. are impossible because they cannot be formed by the sum of three square integers. So these can not be present. So only the proper integers will be used for the value of s, for which your HKL will have a specific value. So for example, your sine square theta, your s values, lambda square divided by 4a square, a, and your HKL. So this is the complete table for the values of your s and values, basically value of your HKL planes. So for a simple cubic system, basically you have your values as 1, 2, 3, 4, 5, 6, 8, 9, 10, and so on. And for your body centered cubic system, you have your values as 2, 4, 6, 8, 10, 12, and so on. And for FCC, you have your values as 3, 4, 8, 11, 12, 16, and so on. And for diamond cubic. Diamond cubic is basically your FCC kind of system only, but it have the atoms which are similar. For FCC, you have different atoms at the corners and different atoms at the face center. So the corner atoms will be different and the face center atom will be different. But for the diamond cubic, your all the atoms are same, carbon only. So this will have the similar kind of S values as FCC, but due to certain things, the cert due to the symmetry and the same elements, certain S values will be neglected and you will only have 3, 8, 11, 16 values. This I'll discuss in the next slide about in more detail about your diamond cubic. But for simple cubic, you will have a whole all values except for these impossible values which I showed you in the previous slide, like 5, like 7, 15, 23, 28, and so on. And for FCC, you will have the values like 3, 4, 8, 11, 12, 16. And for BCC, you can have values like 2, 4, 16, 6, 8, 10, 12, and so on. This is for the cubic system. These values will be different for different kind of systems, like for tetragonal or hexagonal. These will have different values. We are discussing only about the cubic system here. Like diamond has a FC face-centered cubic lattice, but it contains 8 carbon atoms per unit cell. So uh, all the atoms are carbon only. All the reflections have unmixed indices. This unmixed indices is true for your FCC system. So all the reflection have unmixed indices, but the reflections such as 200, 220, 420 are missing in this case because of your presence of your single atom in this case. So this is known as your face centered due to the presence of that reflections which have unmixed indices. Since your FCC, yeah, it's written down in the table. Since your FCC, only those reflections which have your HKL value either all odd, unmixed. What does unmixed means here? This we discussed in last class. Either all odd or all even. So if the HKL values are either all odd or all even, then your FCC HKL plane, that HKL plane will be allowed. Otherwise, if either of them, if they are HKL values are mixed, then the reflections will be absent. So this diamond is known as your face center due to presence of reflections which have unmixed indices. Unmixed indices means either all odd or all even indices. But some extra reflections are missing due to the atomic arrangement in the crystal. Like this 200, 222, these reflections are missing. So as a result, your 4 is absent, your 12 is also absent in your diamond system as compared to your FCC system. So this is the complete representation which I am showing you right now. Let me zoom it in a little bit. Yeah, right now it's very visible. So this is for all cubic systems. Firstly, starting from your simple cubic to body center to face center and then the diamond cubic system, and one is shown for your hexagonal system. So for simple cubic, you know all the, and your y-axis shows your distance on film or chart. So this basically is the diffraction patterns for various lattices. So for simple cubic, you will have your reflections along 1, 2, 3, 4, 5, 6, 7 won't exist at all in any of these case. You can see that 7 doesn't exist and it will exist cubic will be simple cubic will be there. For body center, you will have 2, 4, 6, 2, 4, 6, 8, 10, like that. And for your face center, you can see you are having the reflections along 3, 4, this 4, 8, 11, 12, and so on. And for diamond, this 4 1 is missing because this 4 1 corresponds to 200, and also this 12 1 corresponds to your 222. So these reflections are present for your face center but are absent for your diamond cubic system. This will be different for your hexagonal system. For hexagonal system, you will have different kind of values which you can see from this figure. I guess this value of S and all these things are clear to everyone. If you have any doubt, then please let me know. Otherwise, we'll move towards the next part. If you don't have any doubts, then I'll proceed further. So further, we'll do this quantitative analysis using your X-ray analysis. So for the X-ray, we'll do this quantitative phase analysis. So basically, there are different ways to you do this quantitative phase analysis. The first one is the external standard method, where the line from pure component, or we can say pure alpha component, is used. And the second one is your direct comparison method. Direct comparison method, where the reflection from another phase is used, which is present within the mixture. And the third one is your internal standard method. This internal standard method, here the reflection is used from the foreign material, foreign material, which is mixed with your specimen itself. So base, and your last one is your reference intensity ratio, which is known as RIR. So this is basically generalized internal standard method developed by the ICDD. So ICDD is basically the database. So they have developed this method. So basically these all methods are used for the quantitative phase analysis. And we, in this today's, so basically these are your external standard methods, direct comparison method, and internal standard methods. And they are using different reference line for their analysis. And today we'll use this direct comparison method for certain calculations. We'll study this direct comparison method in much detail. So basically the intensity, the quantitative analysis is basically given by your intensity, and your intensity depends upon your concentration, intensity depends upon your mass absorption coefficient, and so on. So for your pure substance, you have your intensity of your HKL plane given by this long equation, where the long equation is described as your intensity of a certain HKL plane, intensity of your certain HKL plane, or you can say your integrated intensity is given by I naught e raised to the power 4 divided by m square c to the power 4 into lambda cube a divided by 32 pi r into 1 by v square into modulus of f whole square into p into 1 plus cos square 2 theta divided by sine squared theta cos theta into e raised to the power minus 2m divided by 2 mu. So this is the complete equation to describe the intensity. So basically here your I will be basically your integrated intensity and your I naught will be your intensity of your incident beam. This E, M, C are basically the charge of E is basically the charge of electron, M is mass of electron, and C is the velocity of light. Your lambda is the wavelength of incident radiation, and your A is your cross section area of incident beam, and your R is basically the radius of your diffractometer circle. This diffractometer circle also will discuss in the later slides, that how can we see, depending upon the geometry of your system which you are using, you can have different diffractometer. And your V is your this V is your volume of your unit cell. F is your structure factor, which we discussed in the last to last class, that for different crystal systems you will have different structure values, and depending upon the atoms present you can have different structure values, which will tell you about the intensity. This P is basically your multiplicity factor. This multiplicity factor P means that if your plane is 111, multiplicity means P is your multiplicity. This means that all the family of this 1 plane will be included in this intensity. Like for 111, let me erase this. Like for 111, yes, it will include all the family like 111, 11, 1, all bar 1, 1, bar 1, 1 bar 1, 1, bar 1, 1, 1, or 1 bar 1, bar 1, bar 1, 1, bar 1, or bar 1, bar 1, 1. So these all planes, these are total 8 planes. So these all are included in the family of this 1 plane. So this 1 plane have a multiplicity factor of 8. So similarly, different family of planes have different multiplicity factor of their own. So this P is your multiplicity factor, and this theta will be your Bragg angle only, and this your e raised to the power minus 2m is basically your temperature factor. This exponential one is your temperature factor, and this your 1 by 2 mu is basically your mu is basically your linear absorption coefficient. So basically this is the whole equation for a to cal to evaluate the intensity, to tell you about the intensity of your pure substance. Let me erase all this. So this is basically the integrated intensity value for a pure substance. And when this your intensity is given by, and for a mixture, your intensity I alpha is given as K1 divided into C alpha divided by mu m, where your K1 is a constant and it is unknown. This K1 is a constant and unknown value. So we will use that second method which we discussed in the last slide, the direct comparison method, where we will use this direct comparison method where the reflection from another phase within the mixture is used. So for your direct comparison method, firstly we have your K2 given by I naught e raised to the power 4 divided by m square c raised to the power 4 into lambda square lambda cube to the power, this is lambda cube a divided by 32 pi r. So this is represented by your K2 and your R term is represented by 1 by V square into structure factor whole square into multiplicity into 1 plus cos square 2 theta divided by sin square theta cos theta into e raised to the power minus 2m, or we can say exponential of minus 2m. So now we are representing these long terms by the K2 and R terms so that we can write the diffracted intensity I as K2 into R divided by 2 mu. So this K2 value, K2 in this equation, K2 is a constant value and is independent of substance which is present in the mixture, and your R and your R term in this equation, this 14.11, this equation, your R depends upon theta, depends upon HKL, and also depends upon the substance. So these two terms are separated in such a way from the long intensity equation which we discussed in the previous slide. These terms are separated in such a way as K2 is a constant value which is independent of the substance, and R value depends upon theta, HKL, and the substance altogether. So when you have a mixture which is having two different phases like alpha and gamma phase, so for this kind of mixture, your one phase will have an intensity I gamma will have intensity K2 R gamma C gamma divided by 2 mu m, and your alpha will have intensity I alpha is equal to K2 R alpha C alpha divided by 2 mu. And when you will divide these two, you will get I alpha I gamma divided by I alpha is equal to C gamma C alpha divide R gamma C gamma, sorry. So basically your intensity, when you divide these two equations for different composition, for different material, different phases present in the mixture, you will have I gamma divided by I alpha is equal to R gamma C gamma divided by R alpha into C alpha. So this basically is your main equation which can be used further if you are having a mixture of phases. So the value of this C gamma divided by C alpha can be obtained just by measuring the intensity ratio of your C gamma and C alpha, and calculation of this can be done to calculate this R gamma and R alpha separately. So once you have this C gamma by C alpha value, you also have this additional relationship that together, if your mixture is having only these two phases, alpha and gamma, then the concentration of both these phases, the sum of concentration of both these phases will be equal to 1. So this is another equation, another relationship which you have. So basically from this you can remember that your whole intensity equation which discussed in this for a pure substance like this, it's broken down by this K2 term and R term, where your K2 term is a whole constant value which does not depend upon the type of substance which we are looking in the system, and your R2 value and your R value depends on theta, depends upon 2 HKL value, depends upon the substance which that you are looking for. And for the mixture, like for a two component, this is for a two component. And if you are having a three component system, for a three component system, this equation will be C alpha plus C gamma plus C beta will be equal to 1. So depending upon the component, firstly you can have the intensity, like for alpha gamma phase, your intensity is given by I gamma into K2 divided by 2 mu m into R gamma C gamma. And for alpha, you have I alpha is equal to K2 R alpha C alpha divided by 2 mu m. And when you divide these two equations, you get simply, I'll just erase these things. So by taking the ratio of both these intensity equations, you will get this simple intensity ratio with the R and concentration. And this is your another equation for your two component mixture. So with this thing, this intensity thing will end over here, and I'll discuss briefly about how the orientation of your detector and how the complete orientation basically of your XRD instrument is being done, and how we can have different orientations for the same X-ray analysis. So basically, this is the basic schematic for your X-ray diffractometer, where your sample, I'll just represent by this blue color. So this blue one is your sample, and your incident line is your S1, and it goes like this and falls on the sample, and then it is reflected back and it goes in this direction. It falls on the sample at an angle of theta, and it get reflected back by the same angle theta, and it is went to the detector. So this part is your detector. This is your incident beam. So the direction of your incident beam with your powder sample plane is theta, and their reflected beam is also having the same angle. But if you consider the angle of your between your incident beam and your diffracted beam, I'll try to make it here for much more clarity. Suppose this is your incident beam This is your sample. It is making an angle theta over here, and then your reflected beam is also making an angle theta with your plane of your sample. Then to calculate the angle between your incident beam and diffracted beam, I'll extend this incident beam. Then this angle will be also theta. So the angle of your incident beam and diffracted beam, this complete will be 2 theta. So which is represented over here. If you can see it clearly right now. So your detector, this one, can move from here to here to change your theta values to have your intensity at all angles. And as a result, this one is complete is your diffractometer circle. This I'll try to show it in different color for your convenience. Yeah, let me make it this green one. So this whole one will be your diffractometer circle, and your detector will revolve around this diffractometer circle to get the intensity from different angles from your sample. So this is known as your Bragg-Barnato diffractometer. Next you have this focusing camera geometry, where your incident beam is at point A. It is getting incident on certain point and it is getting reflected to a point B. Then your powder sample is present in this whole location from point P to P dash. So your incident ray will be in this direction. So as a result, it will get reflected back to this point B. So this angle of your between your incident beam and diffracted beam here is alpha, and in the according to the geometry, this angle will also be your similar, which will be alpha only. And as we know, this angle is your 2 theta, that is double of your Bragg's angle. So see this focusing camera geometry in the right hand side, which I have drawn, where you have this your incident beam represented by this S, and this is your complete powder sample from point P to point P star. So your first ray will go like this. It will get reflected to a point T dash, and your angle between these two will be 2 theta 1. Similarly, it will go to a different point. It will get reflected at the same point, and similar for the third ray. So these all are the incident and these all are the reflected rays which are reflecting at a similar point D1. So the angle between the incident and the diffracted will be same in all the case, will be 2 theta 1. So similarly, if your if your detector is being shifted from point D1 to D2 in this case, like at point this will be point D2. So now if your incident beam is same only, because your sample is at a constant position and your source of electron beam is also at source of X-ray is also at a constant position, only your detector is being moved from point D1 to D2. So then your reflected ray will be detected only when it is coming to point D2, this one. And for this point, it will be this one, and for this point, it will be this one. So this will have a, let me make it much more clearer by changing the color. So this will have a different theta value. This one, this one. This will have your, basically you can say, 2 theta 2 values. The initial red one was having your, sorry, I'll represent with the red only. So basically, when you are shifting your detector from position D1 to D2, your angle will change. So you can have different intensities at different angle value. And you all know that 2D sine theta is equal to lambda. So 2D is fixed for a given HKL. So for a given HKL, at this point, your 2D is fixed, and when you are changing the direction, you can get different D spacings. So the next one is your focusing geometry for flat specimens in the forward reflection and in the back reflection. So basically, in your forward reflection, your incident beam, similar to the previous one, this will be your sample. So your incident beam will be like this, and it will get reflected back to point F dash. So this complete will form your focusing circle, and this whole will be your diffractometer circle. The diffractometer circle and your focusing circle are two different things. Just keep these things in mind. So this whole circle is your diffractometer circle, and this inner part basically simply is your focusing circle. So this circle is your focusing circle, and the outer circle is your diffractometer circle. So similarly, for the back reflection, when you are having at a higher theta value with your powder plane, this theta, this will be similar. So your focusing circle is much more clearly visible in this case. So this will be your focusing circle, and the outer one will be your diffractometer circle. So basically, among all the possible orientations of each of the possible HKL planes, the one which are nearly parallel to the surface of the specimen are in the right orientation for collecting the focused Bragg diffracted beam at the diffractometer circle. So basically, you are having your specimen like this. So only those planes which are parallel to the surface of your specimen. So only these planes will follow or will allow, sorry. So if this is your specimen, so only these planes which are parallel to your surface of your sample will reflect in your XRD and will follow Bragg's condition. And if you want different planes, such as these kind of planes in your specimen, if your specimen is like this and you want these planes to be reflected, then this can be done by rotating the specimen normal in the plane of the diffractometer. So we are basically scanning all the possible 2 theta values limited by the design of the experimental setup in the experiment. So we can either change the position of your detector, like in this case, or you can change the or you can rotate your sample itself to get the despacings or the intensities which will follow the Bragg condition from different planes of your sample. Also, you have one more theta to theta diffractometer. So this basically I'll not discuss in much detail. So basically this is your initial one, this black one, which is represented by this S line, whose normal is also given by this black N, and this is your incident beam, and this is your reflected beam. So in this case, you have a flat specimen. So if you rotate the specimen by a certain degree, like this, I'll just zoom it in to tell you. This red one, which I have already marked, actually it was much more clearer with the black line itself. Yeah. So this black one is basically your initial S1, and when you rotate it with a certain angle of this omega, this S dash will be there, which is this red one. So if your specimen is rotated by an omega degree, your detector which was earlier presented here, it should be rotated by double angle, as the rotation of your sample. So here the sample is simply rotated by this omega degree, and your detector need to be rotated by the 2 omega degree to capture the reflected beam from your sample. So this arrangement is known as theta to theta diffractometer. And in the last, we have these X-ray filters, where initially we discussed that for the X-ray generation, we can have different K alpha, K beta values depending upon from beam, which shell the electron is being emitted to go to the K shell. So K alpha will be the one where the electron from L shell will jump to the K shell, and K beta will be the one where the electron from M shell will jump to the K shell, like this and so on. So in one, we will have the combination of both K beta as well as K alpha radiation. So basically, we need to have only a one single value to get detected. So we use these X-ray filters. So basically the monochromatic radiation is used for the analysis of this case. So we require filter. So in this case, generally I told you we use copper K alpha radiations, right? Which have a wavelength of 1.54 angstroms. So this copper will also emit K beta, and to block that, sorry, and to block that K beta radiations from K alpha, we need to apply certain filters. So this undesirable wavelengths can be suppressed by passing the beam through filters which absorb edge lines just above the parasitic wavelength. So this nickel filter is used, which will absorb this K beta spectrum. So only K alpha line will go to the sample. So different metals. So when your target metal is molybdenum, you will have zirconium filter. When it will be having copper, you will have nickel filter. So depending upon your target material which you are using, you can have different kind of filters. Like for cobalt, you can have iron. For iron, you can have manganese, and for chromium, you can have vanadium filter. Is this thing clear to everyone? I'll just give you 2 minutes. Then we'll discuss further with the assignment things. If no, then I'll go to this practice assignment of this week 9. So the first question says the X-ray diffraction cannot be applied to study the texture in the material, the magnetic structure, the nanoregime crystal size, microstrain in the material, or the dislocation density. Can anybody tell the answer? Can anybody try? X-ray diffraction cannot be applied. We have studied all the things which can be answered using this X-ray technique. Sarvana Devi says B and Shailendra says A. Let's see. Texture in the material can be told, no, Shailendra? We discussed, I guess. If you have your intensity versus 2 theta X-ray plots like this, if your one peak is having a very high intensity as compared to other, that means that it is textured along that plane. So this texturing could be answered. The right answer is this magnetic structure. So B is the correct answer for this question. This cannot be answered using the X-ray diffraction. The next question says the peak indexed in the diffraction pattern are 110, 200, 211, 220. The indexed phase represents dash crystal structure. Anyone? Will this be BCC, FCC or hexagonal? The sum of all these are even. This is having a sum of 2, this is also 2, this is 4 and this is 4. So this condition was valid for your BCC system. So correct answer will be option A. The next question says that the material for which you want to quantify the phase fraction is alumina and silica. When you mix a foreign substance like magnesium oxide, the method of quantification is called what? So for a foreign substance we discussed, no? That will be your internal sample method. So option B will be the correct answer for this case. We discussed, no, among the 4 methods that for internal sample method you will use the foreign substance reflection. So in this case, internal sample method will be the correct answer. The question number 4 says, among the following options, choose which is the ratio of h square plus k square plus l square for a diamond cubic structure. This also we discussed in today's lecture. Can anybody tell me the answer? Is anyone guessing? Yes, D. Very correct. It will be 3, 8, 11, 16 for a diamond cubic structure. Here, certain peaks corresponding to FCC won't be present. Remember, no? For the diamond system. So D will be the correct answer for this case. The next question says, statement A says, the residual strain is measured from XRD and stress is measured, sorry, the residual strain is measured from XRD and stress is calculated from the measured strain. This statement is completely correct. Strain we can calculate from XRD and stress is calculated from strain. This we discussed in the second slide itself, I guess. And the statement B says that the residual stress analysis is based upon the despacing variation caused in the material during deformation. So depending upon the despacing, how much it has, so initially if it was D naught and if it has been increased to D1, then it will have a impact on the position of your peak. So depending upon that, you can have calculate your stress. So both these statements are correct. So correct option is option C. Both statements are true. Is there any doubt in this practice question? Otherwise, I'll take a 2-minute break. I need to get water. Then we'll start with this quiz part. Sorry for this inconvenience, please. Yes, sorry for the inconvenience, guys. Is there any question, any doubt? No? Then we'll start with this quiz of this week 9. The first question says that the intensity of X-rays diffraction peak of a particular phase is dash to the concentration of that phase. This we discussed, I guess, in the long equation. Or you can also remember the equation where we compared the intensity of the ratio of intensity for the mixture, where we wrote that I gamma divided by I alpha is equal to R gamma C gamma divided by R alpha C alpha. Remember? So from here also you can write simply that your intensity will be directly proportional to the concentration of that phase. So this option B will be the correct answer for this case. The question number 2 says, which of the following statement is or are correct for the Rietveld method? So this is basically the refinement method. The statement 1 says that refine information about a single crystal structure. Yes, this is true. It This is basically the refinement method which is used to calculate the accurate parameters of your system. How much stress or strain is present. All these things can be calculated using this Rietveld method. So basically, the statement 1 says that refine information about the single crystal structure. Yes, this is true. The statement 2 says refine information about the single sample. Yes, refine information about the multi-phase. Yes, this is also true. So this is basically just the refinement method. So basically, all of 1 to 3 are correct. So option C is the correct answer. Question number 3 says the examination of X-ray diffraction data for bentonic steel shows two phases, alpha ferrite BCC and gamma austenite FCC. The integrated intensities of 110 ferrite line is 25 and the 111 austenite line is 3, both in arbitrary units, because intensity doesn't have any units of its own. It is always represented in, whenever we plot a XRD in x-axis, we write 2 theta, which we generally represent in degrees, and on y-axis we represent intensity. In bracket we'll write AU. AU means arbitrary units. So basically, they calculate the volume percent of the retained ferrite in steel. So basically, I'll just try to write the things which are given in this question. So basically, the mixture of two phase alpha ferrite and gamma austenite. For ferrite, you have been given the intensity as 25, and for austenite gamma phase, you have been given intensity 3. Calculate the volume percent, and you have also been given R alpha divided by R gamma as 1.5. So basically, you need to calculate the volume percent of your ferrite in steel. So ferrite means your volume percent of alpha. Volume percent we can simply relate it to the concentration. So basically concentration of alpha need to be calculated in this case. So since we know the formula that I gamma divided by I alpha is equal to R gamma divided by R alpha into C gamma divided by C alpha. So you have this R gamma as 3, I alpha as 25, and then when you will cross multiply this R gamma divided by R alpha, it will become R alpha divided by R gamma, it will become 1.5. So you will have C gamma divided by C alpha. So when you will clear this out, you will basically have 3 into 1.5 divided by 25. Or basically, you can just for your convenience, you can write C alpha divided by C gamma will be 25 divided by, and 3 into 1.5 will be 4.5. So this will come out to be 5.5. So basically your C alpha will be 5.5 times C of gamma. And we know one another equation where C alpha and C gamma, the sum of these two will be 1. So when you use this, you will get 5.5 C gamma plus C gamma will be 1. So C gamma will be 1 divided by 6.5. So 1 divided by 6.5 is basically your 0.15. So in percentage, or so your C alpha will be 1 minus 0.15, that will be 0.85. So I don't know if I am doing any mistake or this is incorrect, but C alpha, if I'll write in percentage, it will be around 85%. So the closest to this is this option A, 75%. So according to me, option A should be the correct answer for this case. Fine. Yes, simply use this ratio formula which we discussed in today's class, and one this formula where C alpha plus C gamma will be equal to 1. Just simply put the values in this equation. Then I got this 85%. It is closest to this. I don't know if I am doing some mistake in the calculation or something, but this is the closest which I am getting. So in my opinion, option A should be the correct answer for this question. If you have any thoughts or any comments, please let me know. Any doubts, any comments? No? Then I'll move to the next question, which says, I'll try to erase this. Next question says, which of the following statement is or are correct microstructural information in quantitative XRD analysis? Statement 1 says, smaller crystallite size in nanocrystalline materials. Yes, this information can be tallied by your quantitative XRD analysis using your Scherer formula and all. The statement 2 says, an inhomogeneous composition in a solid solution. Yes, this we discussed in the previous question itself. Composition can be calculated. The statement 3 says, so statement 1 is correct, statement 2 is correct. Statement 3 says more stacking faults, more microstrain and other defects in crystal. Yes, this can also be done. This information can be gathered using this quantitative XRD analysis. So statement 3 is also very correct. The statements. So you can all use Williamson Hall plot or Williamson Hall equation for this stress strain things. And the statement 4 says the peak broadening. Yes, this information is also being captured by using your XRD analysis. So all the statements are correct in this case. So option D is the correct. All these statements are correct for this question. So the question says that which of the following statements are correct microstructural information. So all these informations are being captured from your quantitative XRD analysis. So next question number 5 says what strain is required to cause the total peak broadening as FWHM is equal to 0.006 radian, assuming theta is equal to 60 degree, lambda is 1.5 angstrom, and crystallite size is 1350 angstrom. Hint is also given in this case, which we also I guess we discussed or not, I don't remember. This Williamson Hall equation is there, which is represented by this B is equal to zero point 0.9 lambda divided by T cos theta plus 4 epsilon tan theta, where your theta epsilon will be your the value of your strain. So basically your FWHM B value. FWHM is basically what? Your B. So B is given as 0.006, zero point 0.9. Your wavelength is also given as 1.5 divided by crystallite size. Crystallite size T is given by 1350 angstrom and cos theta. Theta is 60 degree plus 4 epsilon tan 60 degree. So when you will, can anybody solve this term? Only this term, zero point 0.9 into 1.5 divided by 1350 into cos 60 degree. So that we can take it to the left hand side and then subtract it from 0.006. Can anybody calculate this value? This value, anyone? So this will come out to be 0.006 minus 0.002 and your this will be equal to 4 epsilon and your tan theta is basically what? Under root 3. So when you will rearrange all this, you will get 0.004 divided by 4 into root 3 will be your epsilon value, which epsilon will come out to be 0.00057, which is very close to, or we can approximate it to 0.001. So according to this, option B should be the correct answer. Anybody got this 0.001 as their answer? Anyone in the class? Yes, Shailendra. C alpha is C alpha. Which question you are talking about? Okay, this is the previous one, I guess. Yeah, you are. Yeah. 0.002. I guess you sent it very later. Yeah, it was 0.002, and then you subtracted it from the 0.006, that is from the B value. You got 0.004, and when you divide this 0.004 with this 4 and under root 3, you will get 0.00057, and you can write it approximately equal to 0.001. So epsilon, the strain, could be 0.001. So option B should be the correct answer for this case. The next question says, which of the following statements is or are correct about quantitative analysis by lattice parameter method? So the first statement says applicable for continuous solid solutions. Yes, this statement is completely correct because your lattice parameter method, I guess we have not discussed much about this, but it is used for your continuous solid solutions. It is used to determine the composition of single phase, not amounts. Yes, this is also correct. The third statement says that accurate method of determining the chemical composition. Yes, the lattice parameter method is used for this purpose as well. So, according to me, option C, all statement 1, 2, and 3 should be the correct statement for this. We didn't discuss much about this, but this question itself tells that what things can be done from this lattice parameter method, that it is applicable for your continuous solid solutions. It is used for the determination of your composition of single phase, not the amounts, just the composition. And it is used for the accurate measurement of your chemical composition in your mixture sample. Question number 7 says, if the size broadening is the only contribution to the peak width, what will be the Williamson-Hall plot look like? If size broadening is the only contribution to the peak width. This I guess we discussed, remember? If size is the only contributing factor, then Williamson-Hall plot is basically what? B cos theta on the y-axis and sin theta on your x-axis. It was having a plot like this and this. This I told you for your when only size is contributing, and this was for only strain contribution. So they have asked for the if only size broadening is the contributing. So if only is only contributing, then you will get this horizontal line of WH plot, where WH plot is basically B cos theta versus sin theta. So option A says a line, a linear line having zero intercept on the y-axis. No, it has a certain intercept. A vertical line is this one, this dotted one. This we draw is the horizontal line. Linear line? No. None of these is the correct answer. So option D will be the correct answer, I guess. Because it is horizontal line with a certain B cos theta value. Constant B cos theta basically. Constant B cos theta value. When size is the only factor which is broadening your peak in your XRD. The question number 8 says, which of the following statements is or are correct about quantitative analysis by method of standard additions? Statement 1 says, the peak intensity is first measured on the phase of interest then again measured the intensity after adding the small amount of this phase. The statement 2 says, also known as spiking method. Statement 3 says, also known as doping method. I guess Professor Heaven must discussed about this method, but this standard edition, all these statements are very much correct, which I'll just repeat for you guys, that for the standard addition method for the quantitative analysis in the XRD, the peak intensity is first measured for the phase of interest, then it is again measuring the intensity after adding the small amount of another phase. And then statement 2 says this is also known as the spiking method, also known as your doping method. So in this case, option D should be the correct answer, which says that all the statements are correct. The question number 9 says the following statement is true or false. The absorption method requires the measurement of intensity from a diffraction peak in the mixture and from a pure standard material. Absorption method. This one was the standard method. Last one was the lattice parameter. So this question says the absorption method requires the measurement of intensity from a diffraction peak in the mixture from a pure standard of a material. This statement is completely true for absorption method. Basically, this I guess professor discussed in his class, is requires the intensity from the diffracted peak of the mixture and from the pure substance. So only the diffracted peak from the pure mixture can't tell you. You can just have the diffraction peak from your pure substance. Then you can use this absorption method for further analysis. So this statement is completely true. The next statement says, the last question is, the following statement is true or false. The statement is, a perfect defect-free single crystal, the XRD peak profile shows diffuse peak. For a perfect defect-free single crystal, the XRD peak profile will show the diffuse peak? No. For a perfect defect-free single crystal, it will show not the diffuse peaks, it will show your sharp peaks. So this statement is false, so option B should be the correct answer. For a defect-free perfect single crystal, you will have the sharp peaks like this. You won't have this diffuse peak for a single crystalline defect-free perfect crystal. So I guess these questions are clear to everyone. If you have any doubt on any of the question or any of the theory part, please let me know. Thank you all for attending the class. If you have any doubts or any comments, please let me know. VTY, are you there?